Right, guys, so welcome back. Now, this is question 6 of the same paper, 2018, Feb March. Let's begin. Now, we have sodium hydroxide, which is neutralizing an acid. We have H positive ion reacting with sodium hydroxide OH negative ion to form water. So, this is an example of neutralization reaction. Okay, because this is an acid reacting with an alkali forming water. Now, in a 11,000 GMP sample of an aqueous solution, the concentration of an acid is this much. What is the mass of the solid sodium hydroxide? Neutralizes this acid. Okay, so we just need to find out the mass of sodium hydroxide required to react with this particular amount of acid. The very first step is to find out the number of moles of the acid that we have. All right. So concentration formula was concentration equals moles upon volume. So moles is equal to concentration into volume. So let's just calculate that. The concentration is 1.26 raised to the power of -3 multiplied by 11,000. Correct? So 3 zeros and the -3 goes out. And 1.26 into 11. Just do this. It's turned out to be 13.8 x moles. Now we've got the moles of each positive ions. Let's calculate the moles of OH negative ions. So because the mole ratio is 1:1, therefore OH negative ions will also have an exact same number of moles. What about sodium hydroxide? Well, each mole of sodium hydroxide contains 1 mole of sodium and 1 mole of hydroxide ions, correct? So 1:1. The ratio is still 1:1. So the moles of OH negative ions is the same as the moles of NaOH. So these are also the moles of NaOH. Now you have the moles of NaOH as well. All you need is the mass of NaOH. In order to calculate the mass is equal to moles into MR, right? So moles of NaOH multiplied by the MR of NaOH. What's the MR of NaOH? MR, sodium hydroxide. So Na is 23 plus 16 plus 1, right? Student. It's turned out to be 554 grams. So option D. Option 6 is option D. And yes, that's it, Scarborough. Okay. Hope that you. Now, question 7 is from gas laws. Gas laws can be summarized by PV equals nRT. This is the equation, the ideal gas equation that you need to know and you need to summarize. Okay, and you need to learn actually on your fingertips now. 0.96 grams of oxygen gas. Now, remember, this is gas, so it's O2. It's contained in a vessel of this much volume. Now, volume is 7 raised to the power of -3 meter cube at a temperature of 30 degrees. Now remember, this is in degrees Celsius. Assume gas behaves as an ideal gas. What is the pressure of the vessel? All we need to do is just use the formula PV equals nRT, but you need to be very, very careful because you need to convert everything in this SI unit form. Now let's look at all the different quantities that we already have. All we need to do is just find out the pressure, make the subject. It's going to be nRT over capital V over volume. Now, n is the number of moles. Do we have moles? We don't have the moles, but it's okay. We can find the moles, right, from here. Now, moles is equal to mass over MR. So, it's 0.96 divided by MR. It's 2 multiplied by 16. So, 0.96 upon 32.96 divided by 32, which is 0.03. We have 0.03 moles of oxygen. We have the moles of oxygen in here. All right, the first quantity solved. R is 8.31. Remember that. In SI units, it's 8.31, and that's it. Temperature needs to be converted into Kelvin as well. So 30 needs to be added to 273. So it's going to become 303 Kelvin. Remember, you need to convert the temperature into Kelvin. What about the volume? Volume is already given in SI units in meter cube. So let's put everything in this equation now. Let's put everything in this particular equation. The moles are, wait, where did the mole go? Oh, oh, here they are, 0.03, 8.31, 303. Volume is 7 raised to the power of -3. Let's turn out, let's calculate the answer now. 0.03 into 8.31 into 303, all divided by Wait, it's 303, not 303 squared. Okay, divided by 7 raised to the power of negative 3. Okay, so this is 1.08 into 10 to the power of 3 Pascal. So 1.08 raised to the power of 3 Pascal, the 1.07 raised to the power of 3 Pascals. Now raised to the power of 3 is Kelvin, right? Kilo, right? 1.08 kilopascal. So which of these is the closest answer? Is option A. Wait, that's not the correct answer. I think there's some calculation error because this is the answer, and yeah, we are getting this, but there's just some. Oh, wait. It's not 1.0. My bad. It's not 1.08. It's actually 10.08. Yeah, 10.8. 10.8 into 10 to the power of 3 pascals. So, yep, that's correct. It's option C. 10.8 kilopascals. Yep, option C is correct, not A. Right, calculation error. Question 7. Now, after question 7, you've got question 8 now. All right. Now, question 8. Which equation represents the standard enthalpy change of formation of water? Now, remember one thing, you need to know, in order to solve this particular question, you need to know the definition of standard enthalpy change of formation. Now, standard enthalpy change of formation, first of all, is standard. Standard means it's under standard condition. Secondly, it's enthalpy change of formation. So enthalpy change of formation, and with a standard sign, standard enthalpy change of formation of anything, any compound, is actually the enthalpy change when a compound, for example, if you talk about sodium chloride, so when this compound is formed from its elements. So sodium and chlorine are the elements, and you only get 1 mole of that particular compound. Then this enthalpy change is considered the enthalpy change of formation. All right. So similarly for water, we have hydrogen and oxygen combining together to form water. All right. A little half, and yeah, that's it. This is enthalpy change of formation of water. Okay. So you have 1 mole of water being produced from its elements under standard conditions in the standard states. That's the definition of enthalpy change of formation. So let's look at it. Let's compare it with all of these. The equation that is the same as this one is the answer. So yep, you have 1 mole of water, you have half moles of oxygen, you have 1 mole of hydrogen gas. Yep, option B is correct answer. Question 8, option B. Question 9 now. Hess's law and bond energy can be used to calculate the enthalpy change of a reaction. Now, bromoethane right here can be made by reacting ethane with hydrogen bromide. Now, this is ethene, hydrogen bromide react together, and there you go, you have bromoethane. What is the enthalpy change of this particular reaction? Now, we need to calculate this using bond energy data and Hess's law. Now, bond energy data, where would we get that from? This bond energy data is actually given in the data booklet. Given nothing is here, and because this was a old question, right? Nowadays, they usually don't give the data booklets. This is the data booklet, right? Nowadays, they don't give the data booklet because they already have all the data given in the question paper. But anyways, during these times, you used to get a data booklet in these years. So let's just calculate this particular question using the bond energy values given in the data booklet. I'm going to shift on. These are the bond energy values that we have over here in this data booklet. I think we have a bunch of more bond energy values up here as well. Yep, that's pretty much it. So 2 pages for bond energy values, and let's use them to calculate the bond energy now. Now over here, we need this enthalpy change of formation, right? Enthalpy change of this particular reaction. Now, always remember one thing, whenever you need to calculate the enthalpy change of a reaction, and whenever you have the bond energy data given to you, there's just one simple formula that you need to apply, okay? Bond energy data is always given to you, just one formula. In order to calculate the enthalpy change of reaction, all you need to do is just do the enthalpy change of reactants minus the enthalpy change of products. बस that's pretty much it. Enthalpy change of reactants minus enthalpy change of products. अब ये कैसे करेंगे? How would we do that? So, well, all you need to do It's just count all the different bonds that are present on the reactant side and put all of their energies together, and then do the same for the product side and put all of their energies together, and then just simply subtract them. Let's look at the reactant side bonds. Okay, so we have ethene molecule. So ethene actually have one carbon hydrogen bond, another carbon hydrogen bond, a carbon carbon double bond, then another carbon hydrogen bond, and a carbon hydrogen bond. So in total, there are actually four carbon hydrogen bonds and one carbon carbon double bond, right? So we have four carbon hydrogen single bonds and one carbon carbon double bond, correct? In addition to that, we also have one HBr bond as well. So that's all the reactants bond energy, right, on the left hand side, minus the product bond energy. Now let's look at the product. So it's bromoethane. So it's CH3 and CH2 and then Br. So this is CH3 and then CH2 and then Br. So carbon hydrogen bond. So we have five carbon hydrogen bonds over here, one carbon carbon bond and one carbon bromine bond here. So we've got 1, 2, 3, 4, 5. Put in all the five carbon hydrogen bonds here, single bonds, along with one carbon bromine bond as well, right? The carbon bromine bond, along with one carbon carbon single bond as well. Yeah. You've put all of these together. All you need to do is just copy the data from the data booklet and plug it in here. So let's do that. Now, carbon hydrogen bond. Let's first find out the carbon hydrogen single bond. So it's right here. It's 410, right? Let's use that value here. 4 times 410. Added to one carbon carbon double bond. Okay, where is the double bond? Right here, 610. What about HBr? Let's look at HBr. It must be up here. There you go. 366. These are all the reactants minus all the products. Now, 5 times carbon hydrogen is already calculated here, 410 plus carbon bromine bond. Now, this might be down here, carbon bromine bond. It's right here, 280 plus carbon carbon single bond finally. So it should be here, 350. Now, plug all of this into the calculator and get the answer. So let's do that. 4 times 410 added to 610 added to 366. That's 2616 on this side minus 5 times 410 added to 280 added to 350. So 2680. So this turns out to be 2616 minus 2680. So this is minus 64. Now see, the thing is kilojoules per mole. With a negative sign, you now know that this is actually an exothermic reaction going on. That's why you're getting a negative sign because, yeah, you already know that enthalpy change of reactions whenever are exothermic, negative, that means it's exothermic. And yep, option B is the correct answer. But now let me tell you something. Now look at this formula very, very carefully. This formula is using reactants minus products. Okay, reactants are the first part of the first component of the equation and products are the second component of the equation. It's not products minus reactants. And always remember one thing, this formula is used whenever you are using bond energy data. Okay, bond energy data will always require this formula. There's another formula as well in which you do the products minus reactants, but in that case it's not the bond energy data that you use, it's the formation data that you use. It's something different. So if we come across that question, and we will, because there are hundreds of questions from that concept as well. So we are going to go over that concept as well. But you have to do reactants minus products. Only then will you get the correct sign as well. Okay, only then will you get to know that, yeah, it is actually an exothermic reaction. Okay, so reactants minus products. So question 9, let me just quickly check. Yep, it's B. That's correct. Is everything clear so far? All right. Now, question 10. Last question of this video. Which reaction is not a redox reaction? Which one is not a redox? Remember, it's not a redox. Now, for something to not be a redox, redox actually means it's reduction oxidation reaction. So both of them have to be occurring at the simultaneously. In the first equation, you have magnesium going from 0 to +2. So yep, it's all getting oxidized. What about nitrogen? Because it's getting oxidized, so yeah, this is redox. Now, next one. Now, in this case, we have magnesium 2 positive. This is 2 positive. All right, then what about nitrogen? So nitrogen here, it's the nitrate ion that we have the nitrogen in, right? So let's calculate this oxidation number. X plus 3 times -2 equals -1. So X equals -6 will go there. +6. 6 minus 1 is +5. So it's going from +5 to plus 4. So yep, it's getting reduced. Nitrogen is getting reduced. What about this one? So yep, it's changing oxidation number for sulfur. And what about this one? I think this might be the answer, because what about, look at the oxidation state of sulfur. It's plus 6 here and plus 6 here as well. So yep, it's not changing. So yep, option D is not an redox reaction, because sulfur is not changing its oxidation number at all. So yep, that's it for this video.